Hi, this is another video that is going to give some more examples of how to apply convolutions, especially the convolution integral when solving equations. This is for differential equations, and so here I'm going to work out or talk through the solutions to numbers 5 and 6 in the practice problems on the convolution handout. So here is number 5 that we're looking at first. It is, we need to solve the equation f of t plus the integral 0 to t minus tau f tau d tau equals t. And so essentially this is asking what is the little f function that is going to make the left side equal t. That's our goal, to figure out what that function is. Using Laplace transforms, take the Laplace of both sides, and so the second line here gives us the Laplace of little f, which is capital F. That's what I wrote in the third line. On the right side, Laplace of t becomes 1 over t s squared, which you could find in your table of transforms. And then in the middle, you have Laplace of this convolution integral. And the convolution theorem says that the Laplace of this integral is going, there should be a 0 there, is going to be some capital F times some capital G. So the little f, its transform is capital F, which means that the t minus tau function, which is just t evaluated t minus tau, its transform is capital G of s. And we know that the transform of t is 1 over s squared. And so that's what you could see I have done on the right side here after the right arrow. So we have f of s, left, right, f of s or plus f of s times capital G of s, but capital G of s is 1 over s squared. And on the right-hand side, we maintain the 1 over s squared, which was the Laplace of t. And so this gives us the right-hand side. Now we need to solve for capital F. And when you do that, you get the fourth line here, which simplifies to 1 over s squared plus 1. And that is a common transform. If you look at your table of transforms, you may have it memorized by now. This is going to be sine of t. If you wanted to check, plug in sine of t for f of t. So you'd have f of t is sine of t first. You'd have f of tau is sine of tau inside the integral. Integrate that and then simplify, and you will see that the left-hand side ends up being t. So this happens to be a simple one to check, and I'd encourage you to do so on your own. Next, let's take a look at problem number 6. And I've rewritten what the equation is that we want to solve. Y prime equals 1 minus sine of t minus this convolution integral. It's an initial value problem with a condition of y of 0 equals 0. So the first thing you do, take the Laplace transform of all parts. So Laplace of y prime is s capital Y minus y of 0, which is 0. Laplace of 1 is 1 over s. Laplace of sine of t, we just saw, is 1 over s squared plus 1 minus the Laplace of this integral. You have a y of tau, and you secretly have a 1 in there. So you do have a product. The y of tau becomes y, and the 1 has a transform of 1 over s. So that's where those two come from. And again, this is from your convolution integral. From here, you solve for y, which I do on the next line. And that turns out to be what I've got over here, 1 over s squared plus 1 minus s over s squared plus 1 squared. And now we want to take the inverse transform of both sides. So inverse transform of capital Y becomes little y. Inverse transform of 1 over s squared plus 1 we know and love at this point, and that is sine of t. And now we need the inverse transform of s over s squared plus 1 squared, which is like one of the problems that I had done on the convolution handout. I had shown that the inverse transform of 2s over s squared plus 1 squared is t sine t, But to get the 2 in the numerator, you need 1/2 outside, or 2 in the denominator. So that's why I wrote that there, essentially multiplying by 1, which is mathematically sound. It doesn't change the quantity. And so we've got sine of t minus 1/2 t sine t. And you could factor out the sine of t if you want, but it's fine to leave it like this. And that would be our solution.